Hello folks, we're back with more math. Today we're going to go into vector fields and we're going to look at the applications of vector fields for calculating the work done by a force field using line integrals. First of all, let's try to define what a vector field is. A vector field is a function that assigns a vector to each point in its domain. In other words, you're putting into this function, we're putting points in three-dimensional space, in four-dimensional space. For example, I took a point in three-dimensional space, and then it's going to output a vector. Okay, so for each point, we're going to get a vector. So we'll use this notation f of x, y, z. This is going to be the vector field. It's a function. As an input, it takes points in space. I put an arrow to show that this is not a normal function. Usually what you do in books is f is bold, okay? But I can't do bold with a pen, so I put an arrow on top of it. It's not a vector, it's a vector field. Okay, for each point, it's a vector. So we're going to say that this function is going to be equal to a function, a three-dimensional function I, three-dimensional function j, and another three-dimensional function k. So as an example, if we just do the two-dimensional version of it, here's a vector field in two-dimensional. It takes its input as xy, and as an output it gives xi plus yj. For example, if I put in 1, 1, I would get this vector at the point 1, 1. I would get the vector I plus j, so we would get this vector. Okay. If I put the point in 1 minus 1, I would get I minus j, so at the point 1 minus 1, I would get this point here, okay? So basically, what this vector field is going to do is, it's going to assign a point, a vector, for each point. So what I can imagine this is, I can imagine a whole bunch of arrows. At each point, I have an arrow, and the arrow is just the vector attached at the bottom to that point. Okay, so the tail of the vector starts from the point, and I just draw the vector for that point. So each point, so I don't have the points here, but they'll be like this. They're going to get bigger like this, and so on. Okay, like this. Okay, so if we think about this one now, at any given point xy, what's going to be the length of the vector? It's going to be x squared plus y squared equals r. So at any given point, the vector is just going to be, you just look at the line, okay, that the point is on, and the length of the vector is just going to be the distance from the origin. That's going to be our vector field. Okay, so it's going to go like this. Okay, so this is a nice looking vector field. Okay, we can do more arrows, of course, like this. Okay, so whole bunch of arrows in that picture. We could have another one. We're doing these all linear so that they're kind of easy to draw. Let's say we have the vector field minus yi plus xj. So for each xy pair, I get another vector. For example, at 2, 1, if I plug this in, what would we get? We would get minus I plus 2j. So it would be this vector. Okay, so at 2, 1, I would get this vector. Now if I draw a whole bunch of more vectors, plug in some more points, I'll kind of get this whirlpool effect. Okay, the vectors on the outside are getting bigger and bigger and bigger. So you get this like water circulation kind of thing going on in that picture if you plug in more points into this vector function. So going back to our formulas, because we're going to look at three-dimensional functions usually, okay? Well, we're going to look at two-dimensional ones also, so don't worry about it. But this m here, okay, it's corresponding to this function x, okay? But it could be, say, x squared plus y plus sine z or something like that. It's just a function of three variables. This n here is, we just have two variables. It corresponds to y, okay? It's just a function. Don't let the letter scare you. And p, we don't have a p here because we're in two-dimension. Obviously, drawing three-dimensional stuff is kind of hard, so that's why I didn't do it. In three dimensions, again, this would be a function of three variables. That's it. For example, I mean, if we want to do something in general, maybe we're not going to be able to draw this, of course. Maybe we have something like this. F of x, y, z is equal to x squared zi plus sine y x j, and maybe plus, I don't know, just let's make something up, a z squared e to the xy k. Okay, so this would be a vector field. Now this guy here, this x squared z here, in our example, this x squared z would correspond to m. Okay, we're not gonna write x y z all the side. So whenever I say m, it's just gonna be the I component. It's gonna be a function. It's not gonna be a constant. This baby over here would be n, and finally this guy over here would be the z component. It's gonna be p. Okay. Again, these are functions, not constants. All right. So the vector fields are great for several things. We already know one thing they're great for, okay, and that's gradients. When we talk about the gradient of a function, it's actually a vector field, isn't it? So remember the definition of the gradient, nabla f, was df dxi plus df dj, df dyj plus df dz k. Now, since f is a variable three-dimensional function in this example, its derivative is a three-dimensional function also, hopefully when it exists. And similarly for df dy, the partial with respect to y and the partial with respect to z. For example, if we just do again a two-dimensional one, if I take the function x squared plus y squared, okay, x squared plus z equals, so this is z equals x squared plus y squared, what is the gradient? Take the derivative with respect to x, you get 2x, and takes the derivative with respect to y, you get 2y, so it's 2xi plus 2yj. Now, this is a vector field. Why? Because for every single xy pair, I get a vector, okay? So it's basically got variables inside its vector, okay? It's got variables inside its vector, so for each point, we get another vector. It's a vector field. And now we already, of course, saw the applications of gradients, right? We used gradients to find max, mins, and all that good stuff. Also Lagrange multipliers. So it's a great thing. It's a great thing. Did we do Lagrange multipliers? Well, I have to check that. Maybe we skipped Lagrange multipliers. We'll do it. If we haven't done it, we'll do it. Don't worry about it. So we have an example of a gradient field that we already know. Now, what is it good for? Well, one of the applications for vector fields is it's good for calculating the work on an object. So let f of xy represent a force field, and let's say C be a smooth curve. Okay, so it's got continuous derivatives, and none of them are 0 at the same time. Okay, so it's a basically nice differentiable function without any quarters. So if we have the force field mi, again, m is not a constant, it's a function, n is a function, p is a function, mi, nj, pk, and let's say we parameterized the curve c with respect to t, let's say it is g of ti, h of t j, and l of t k, okay, for t between a and b, okay, so we have parameterization of this curve. Now, the reason this is not in alphabetical order, of course, is G, H, it would have to be I, but I we're using for the vector. So we have to pick another letter. I picked L. My L is kind of funky. I'm sorry for that. So it's going to be G of Ti, Hj, and L of K. That's going to be the parameterization of the curve. Now, if we want to think about the work done by F over this curve, then the work integral is the line integral over this curve C of f dot product t ds. Okay, so this is a lot to take in. You know, when you first see this, you go like, what is going on here? This is not normal multiplication. Again, this is a vector. This is going to be a vector. If we multiply together at each point, f is a vector, t is a vector at any given point. We're going to do the dot product of two vectors, which is going to be over this curve, and then we're doing this with respect to ds. Now, ds is the arcline differential. So what does this mean? Well, we already know several things, right? That ds is actually equal to absolute value, the speed, the length of the derivative, okay, and the length of the derivative dt, right? Okay, so that's going to help us a little bit. In terms of the physical motivation here, so we have some kind of curve and we have an object maybe moving along this curve, okay? So if I'm trying to move this object along this curve, any force I'm applying except the tangential direction, so in the force in the tangent direction, is going to go to waste, right? Think about it as we've got maybe a bead on a string or something like that, on a wire. Okay, no matter how much I pull it up, the force is going to waste. It can only go in this direction. No, so the only force that's applicable to it is in the tangential direction, in the direction of the tangent. Now, when we're saying the tangent, we're talking about, of course, we're going to say the unit tangent. Okay, so every single force in this direction would be applicable. So we're going to look at the unit tangent. Okay, so the force dot the unit tangent ds, okay, in this direction is going to be our integral. Now let's do some algebra here. F dot t, so t was v over length of v, the velocity, in other words dr dt. Okay, this v is of course dr dt, the derivative of r with respect to t, where r is the position of this curve. Okay, dr dt, v over length of v. Now that's going to be dr ds. So if I plug this into t, I get something nice, and we're going to go from f dot t to f dot dr ds. So the ds's will cancel, and we get another formula for it. This was our original work integral. Now we get over the curve f dot dr. Okay. Again, I have no idea what this means in terms of calculating it. So let's try to get something more friendly. Well, we can do the chain rule. And we can say, well, I can write this as f dot dr as f dot dr dt times dt. Well, what is this? Dr dt is v, right? Dr dt is v. So f dot dr dt, so you can also write this as, f dot v dt. Okay, because this is v. So that makes total sense, doesn't it? Because once you plug in here, if you plug in for ds v dt, and for t v over v absolute value of v, the absolute values are going to cancel, the lengths are going to cancel, and you're just going to get v dt. In other words, dr dt, f dot dr dt. Now here, this integral, because it's not over the curve anymore, because t was parameterized between a equals a and b, this exactly tells you how to calculate the integral, right? So it's not, once you go to t, you know the bounds on t, so the integral becomes a to b f dot dr dt. It tells you how to calculate it. Now I'm going to go 2 steps more. Okay, so this is the most important part right now for us. Okay, this is the most important part for us because it tells us exactly how to calculate this integral. But I'm gonna go 2 more steps. This is gonna be important later on. We're gonna see conservative fields and fields that are not conservative. It's not gonna make much sense right now, but it's gonna make a sense in a few lectures. So what was f? F was m, mi, and j, pk. So this is, if we plug it in, this is m of dx dt, okay, and dy dt. When I do the dot product, right, this is going to be m times the dx dt, okay, plus n times dy dt, okay, and p times dz dt. Because remember, f is this guy, so we could open this up like this. F is this guy, m and p as a vector, dot producted with dx dt, dy dt, that's the dr dt, right? This whole vector, and dz dt. So we get exactly what we have above. Okay, we get this term, right? M times dx dt. Again, m is a 3-variable function. N times dy dt, and p times dz dt. Now, because of the chain rule, when you do, the dt's are going to cancel, so we have this integral. We are losing a and b because it's not, t disappeared. Again, we're going back to curve, whatever that means. Over the curve, we have to do m dot dx, m times dx, n times dy, p times dz. So this is actually very good news. Very good news, because what this is going to equal to is it's going to be 3 integrals m dx plus over c n dy and plus over c over the curve again p dz. Now this just means this was a function. It wasn't a vector field or anything. That m was just a good old function. I need to integrate the function with respect to x, and I need to integrate the y coordinate here n with respect to y, and similarly the k coordinate or the z coordinate of the function with respect to z. So these are good old normal Calc 1 questions. The only problem here is it's over a curve. So what does it mean to integrate the function, okay, to integrate the function m dx over a curve? So we have to think about how we're going to do that. Right now, I'm going to put a question mark here. It looks nice, but it doesn't do us any good right now, okay? So because I can find the antiderivative, no problem. Okay, that's a Calc 1 question. But how do I evaluate it? That's a great question. We don't know how to do that yet. We are going to learn that. Don't worry about it. So the thing that I want you to take away from this lecture is just this is the work done is f dot product t ds, and the way we're going to calculate it right now is we're going to do it from a to b f dot dr dt dt. Okay, so that's the only formulas that you should memorize right now. This is called the scalar differential form. This is going to be useful later on. It's going to be very useful for some vector fields later on. Now I want to talk a little bit about the properties of these vector field integrals. Hold on, maybe I'll skip this and let's just straight away do an example. Let's just do straight away an example and then come back to the properties. Let's find the work done by this force field xyi plus xj plus zk. This is zk over the curve sine t, cosine t, and k. So sine ti, cosine tj plus tk on 0 to 2 pi. So what this is basically, this is a circle when you're looking at from the top, because it's sine ti, cosine tj. That's the parameterization of the circle. But as t goes on, so the height is increasing, so it's basically a spiral coming up towards the camera, okay? It's a spiral coming up towards the camera. So that's the curve we have, okay? So maybe think about an airplane is taking off and it's circling up into the clouds or something like that. So the first thing that we have to remember is if we're trying to calculate the work done on this curve by this force field, the integral that we're supposed to calculate is we're going to calculate c f dot t ds, okay? So I already gave a parameterization. Now, one thing that's important is any parameterization of the curve will work, okay? Any parameterization of the curve will work. Maybe I can just describe this as a spiral. Maybe you parameterize it one way. Maybe someone else parameterizes it a different way. It's always going to give the same answer, regardless of how we parameterize it, as long as we're parameterizing the same curve, okay? So this integral is of course equal to from a to b f dot dr dt. So I need to calculate dr dt on this curve, okay? So what is dr dt? Derivative of sine is cosine. Derivative of cosine is minus sine. So we have cosine t minus sine tj plus k. Derivative of t is 1. That's going to be dr dt. So let's get the dot product. The force field was sine t cosine t. How did I get that? I got this from the curve into x and y here. How am I going to get my x and y? Well, I'm going to only interested in what's going on, what the vector field is doing on the curve, where the curve is at. It's not interested in where else is going on. So if the curve, so this curve was a spiral, but let's draw some curve like this. I don't care what the force field does over here, right? That's not important. It can do whatever the crazy thing it wants to do. What I care is about what it's doing on the curve, where the curve is, okay? So we plug in, we take the coordinates from the curve. This is going to be x, this is going to be y, this is going to be z, and plug it into the function. So x times y is going to be, we saw this in line integrals, it's going to be sine t times cosine t. Y is sine t, and z is just t. Okay, so we have this dot product with dr dt, we get this guy. Okay, dt. So now this good old dot product, so it's going to be sine cosine squared minus sine squared, okay, plus t dt. Okay, so it became just a function of t. Everything else, all the vectors are gone. So now this is a single variable integral. Sine squared, I just divided up into 3 parts. So it's going to be the integral of sine t cosine squared t. It's going to be minus sine squared t plus t. Now this part is the easiest one. The integral of t is just t squared over 2. We want to evaluate that from 0 to 2 pi, so you get 2 pi squared from that part, from this part of it, okay? Now for this one, remember our formula, sine squared was equal to 1/2 times 1 minus cosine t. We have to reduce the power, okay? So we do this, and if it was cosine squared, it would be plus. This is sine, so it would be 1 minus cosine t over 2. Plug that in. And here we can just do a simple substitution. Let u be equal to cosine t. Du is going to be minus sine t dt. So I almost have a du, but it's a minus, so it's going to be minus u squared du. So let's integrate this. This is going to be minus u cubed over 3. In other words, u was cosine, so it's going to be minus cosine cubed over 3. Evaluate from 0 to 2 pi. Well, guess what? That's just 0, right? Plug in, you get, it's going to be minus 1 over 3 minus 1 over 3. It's gone, okay? So this part just is gone when you plug it in. Here we're going to get t times sine 2t over 2. Don't forget the 1/2. Plug that in, and we get minus pi. These guys are going to cancel. We get minus pi plus 2 pi squared. So the work done here is 2 pi squared minus pi for this integral, for this specific force field, okay, and the curve. So I can see vector fields. I can see vector fields as basically a force field. There's a direction and a magnitude at each point. Or I could probably see them as maybe a force field as a fluid moving through space, and we have at each point we have the direction that the fluid is heading and its speed at that direction. Okay, so force fields, or we could have a magnetic field, right? So it gives you the magnetic field, which way the magnetic field is heading and its strength at a given point. So all those good things. When you have a work field, so when you have a force field, okay, when your vector field is a force field, this gives you the work done. When it's a vector field, when it's a velocity field, it gives you something else, which we're going to do next lecture, hopefully. Now, I want to talk about some properties here. Some properties of these vector fields for a second, okay, and that goes back to the line integrals. So I just want to go back to line integrals for just a minute here. So remember that the parameterization of a smooth curve also gives an orientation of the curve. So remember, when we have a parameterization of a curve, we thought about an object moving along this curve. Because it's moving, it gives you a direction on the curve, okay? And it gives you its basically speed, how fast it's moving on this curve. Now, I could give you the same curve, and we could have many different parameterizations. Maybe one parameterization, the object is moving really slowly in this direction. Maybe it's really moving fast, okay? Or maybe it's going the other direction, okay? Now, I just want to talk about what the effect of direction, the orientation on the curve is on line integrals, okay? So when I say the curve C, when I say positive C, it's just oriented this way from A to B, okay? When I say minus C, it's oriented from B to A, from the point B to A, okay? I don't know how fast, we're just talking about the orientation. Now, when we're talking about the specific line integral, this is not a work integral yet. This is just a good old line integral. F of x, y, z, ds. Well, ds is, we know that it's basically dx dt squared, dy dt squared, dz dt squared, so the length of it, basically the velocity speed, square root dt. Now, this is, remember, this always, because it's a square root, it's always positive, okay? So which means, because this term is positive, whether you go this direction or this direction, it's not going to matter, because if you go minus c, you're going to do f of x, y, z ds, well, it's still going to be the same, right? Because this term is always going to give you the positive answer. So when you're doing a good old line integral, it really doesn't matter which way you're going on that curve, okay? Which way, whether you're going from A to B or whether you're going from B to A, it really does not matter. Now for work integrals and any integral of this form, okay, remember this is the same thing as we got when we're talking about this integral, f dot t ds over the curve, it was equal to this guy, right? Without the minus sign, okay? So it was equal to this. Okay, this was the form that wasn't very useful to write yet. So I'm thinking about what happens to these work integrals. Okay, they could be work integrals. They could be other stuff. When we go into velocity fields, we're going to see that they're going to correspond to something else. Unfortunately, when you have, or fortunately in some sense, when you have a work integral, actually you have to slap on a minus sign, so the direction does matter, okay? And that makes total sense, right? So let's talk about the energy and object gains, okay? So if I'm here and I go over here, right? This object gains some potential energy. If I go the opposite way, it loses potential energy, okay? It gains potential energy when I raise it. It loses potential energy. So the integral, from the physical sense of it, they should be just negatives of each other. And the reason here is, well, because we have this ds term here, okay? The ds term here, but now we have a dot product. And we're going to get the integral over minus c is minus the integral over c. Okay? I'm going to give an example of it. Well, I'm not going to give an example of that. I'm going to give an example of this in a second. So the other thing is, we had this assumption for us to be able to calculate these. The curve had to be smooth when we parameterized it. So what happens if it's got corners or stuff? Well, we call them piecewise smooth. Say if you have a corner, something sharp going on, a point where it's not differential, but the curve is generally smooth everywhere else. What you can do is you can break this big curve C into two small curves. C1, this is smooth. C2 is smooth. So when you're calculating any sorts of line integral, what you can do is the integral over C is the integral over C1 plus the integral over C2. Okay, so a piecewise smooth, if you can break it up into piecewise pieces that are in themselves smooth, a curve is called piecewise smooth, and we can still integrate over those guys. Okay, so I have one example, good old line example. This is not a work integral. I have over this curve x plus y plus z ds. Now, because this is not this is just, there's no dot product or nothing going on. This is just the function f ds. Okay, it should be, doesn't matter which way I parameterize it, it should be the same way, give me the same answer. So here we took c to be the remember this was from last class. It's the line segment from the point 1, 2, 3 minus 1, 0, 2. So in our last video, we saw that c can be parameterized, okay, as 1 minus 2ti, 2 minus 2tj, 3 minus tk. And we did this exact integral last time, and we got the answer 21/2. Now what I'm going to do is, I'm not going to go from p to q, and let's say, what happens if we go q to p? What happens if we do the opposite orientation? Okay, in that case, if we're going to go from q to p, remember q was minus 1, 0, 2, p was 2, 2, 1. Sorry, q was, minus 1, 0, 2. P was 1, 2, 3. 1, 2, 3. So n minus beginning, we get 1 minus of minus 1, 2. So it's going to be minus 1 plus 2t. N minus beginning, 2 minus 0, that's another 2. So it's going to be 0 plus 2t. And 3 minus 2, that's going to give me a t. Okay, so it's going to be 2 plus tk. That's going to be the opposite orientation on the same curve. Okay, it's actually a line. Okay, so again, this is for 0 equals t1. Now what I'd like you guys to do, if we have some time, is, well, this is another orientation. maybe get the same get the parameterization where t is between 0 and 2. Okay, as an exercise, maybe that would be great. Get a parameterization of the same curve when t is between 0 and 2. Okay, so when I do this over this curve, again we're going to get 21/2. I want you guys to see it with your own eyes. So if we do this integral, then the r dt this time, well, it's the same as before. Again, it had to be, right? Because ds is always positive. Well, if this is going to depend on, it might give you different answers. For example, when you do 0 to 2, it might give you a different example. But in the long term, when you do the integral, it's going to give you exactly the same thing. The I think is it's still positive. Okay. So I just plug in, I get x from here, y from here, z from here, and then we do for ds, we do 3 dt, okay? And evaluate, then you again get 21 over 2. So whether you go from p to q or q to p, when you're doing a line integral, it doesn't matter, okay? It does not matter. But when you're doing a vertical integral, because of the you have the dot product in there, it matters. Then you get a minus sign if you reverse the direction. All right, that's all I want to say. We worked on force fields. Next time we're going to work on velocity fields, where each point, the vector field is going to represent the velocity of some fluid or something. Basically, maybe it's gas, maybe it's fluid. It's going to represent the velocity of each atom or something at each point. What happens to f dot dt? Then we're going to see funky terms like flux, what the flux means, what flow means, and we're gonna do some more integrals next time. Till then, take care. Bye bye.